Hey everyone, and welcome back to another CloudBridge Tech Labs Explainer. I am absolutely thrilled to have you here for session 6 of phase 1. If you've been following along with our journey so far, you know we are laying down the absolute bedrock of cloud engineering and DevOps. Today, we're tackling the very fabric of how machines actually find and talk to each other across the globe. Before we dive in, just a quick reminder to hit that like button, subscribe to the channel, and make sure you actually complete this explainer's tasks at the end so you can officially advance to phase 2. You ready? Let's get to work.
Real quick, here is our roadmap for this explainer. First, IP address fundamentals. Second, private versus public networks. Third, DNS, otherwise known as the Internet's phone book. Fourth, troubleshooting commands. And finally, your session 6 practice tasks. All right, kicking things off with part 1, IP address fundamentals. Let's talk network identities.
Okay, let's dive into this. At its core, networking is actually incredibly relatable. Every single machine connected to a network needs an address, exactly like a house needs a postal address to receive mail. I mean, if you want to send a letter, you can't just hand it to the postman and say, hey, take this to John. You need the street, the city, and the zip code. Well, computers work the exact same way. For example, your work laptop might be assigned an address of 192.168.1.10, while the local server it needs to talk to is sitting at 192.168.1.20. That unique string of numbers is how the data packets know precisely where to go, making sure that the files you requested end up on your screen and not, your coworkers. To really grasp how this digital postal system works, we need to look at 3 core pieces of vocabulary that make up your network configuration. You're going to see these everywhere in your engineering career. First up is the IP address itself. This is the device identity. It literally answers the question, who am I on this network? Next is the gateway. Think of this as the exit point to the internet, or the front door of your neighborhood. If a device needs to talk to a computer way outside its local network, it sends the traffic to the gateway to handle it. And finally, we have the subnet mask. This defines your network size. It essentially tells your computer, hey, here is the boundary of our local neighborhood. These 3 elements work together harmoniously to tell your machine exactly who it is, who its neighbors are, and how to leave the neighborhood if it needs to. Moving right along to section 2, private versus public networks. Let's look at network boundaries. And this brilliantly illustrates a really strict boundary we have between local networking and global internet routing. On one side, we have private IPs. These are strictly for internal networks, like the devices connected to your home Wi-Fi or the internal servers humming away inside an office building. A classic example is 192.168.x.x. On the flip side, we have public IPs. These are the globally unique addresses used for actual internet access, like 43.x.x.x. Think of it like this. A public IP is like a global GPS coordinate. Anyone in the world can find it. But a private IP? That's like saying conference room B. It makes perfect sense if you're already inside the office building, but it means absolutely nothing to someone on the other side of the planet. Because we only have a limited number of addresses globally, engineers actually created specific blocks of numbers that are reserved purely for internal private networking. These are the 10.x.x.x block, the 172.16 through 17.31 block, and of course the incredibly common 192.168 block. The absolute beauty of these ranges is that they cannot be routed on the public internet. This means millions of households and corporate offices can reuse these exact same internal addresses over and over again without ever causing a collision on the global web. Pretty smart, right? So let's pause for a quick second. I want to throw a question your way just to test your understanding of the boundaries we just established. If you have a machine with a private IP address, say 10.00.5, can that private IP access the open internet directly? Think back to that conference room B analogy. Well, the answer is a hard no. Remember, private IPs aren't globally recognized. To actually access the internet, your local device relies on a process called NAT, which stands for Network Address Translation. NAT acts as the middleman. Your private device sends its request to your router, and the router essentially swaps your private address for its single public-facing IP address, fetches the data from the internet, and hands it back to you. We are absolutely going to explore the magic of NAT in a future session, but for now, just remember, private IPs need a translator to speak to the outside world. Now, how do you actually find out who you are on the network? As a future DevOps engineer, you'll be doing this constantly. Here are the practical, everyday commands you need to find your own machine's IP address. If you're operating on a Linux environment, simply open your terminal and type IPA. If you're on a Windows machine, open your command prompt and type ipconfig.
Honestly, I highly recommend you pause this explainer right now, open up your terminal, and try it. Go find your IP, your subnet mask, and your gateway.
So why does all this matter? Let's look at the real-world stakes for a minute. Imagine you're managing the backend for a massive e-commerce site. You've got an application server sitting on a private IP of 10.0.1.15, and it desperately needs to pull customer data from a database server over at 10.0.2.20. If your routing tables or your security groups between these private IPs are misconfigured, your application servers will just time out. The database won't receive the request, the front end will freeze, and your entire application crashes. In DevOps, mastering these network fundamentals isn't just theory. It's literally the difference between a functional product and total system downtime.
All right, moving into section 3, DNS, the Internet's phone book. Think about how our brains work. Humans naturally remember names and words. You easily remember Google.com or Amazon.com. But honestly, since smartphones were invented, do you even remember your best friend's actual phone number anymore? Probably not. Machines are the exact same way, but they only use IP addresses, like 142.250.x.x. If you had to type in a 10-digit IP address every single time you wanted to check your email or stream a video, the internet never would have taken off. Enter the domain name system, or DNS. DNS acts as the ultimate real-time converter between the easily remembered names we prefer and the machine-readable IP addresses the computers require to actually connect. Let's move to see how this builds into an actual lightning-fast sequence. When you type https google.com into your address bar, what exactly is happening under the hood? It's a 3-step dance. Step 1. Your browser essentially raises its hand and asks the DNS server, hey, I'm looking for google.com, what's the IP address? Step 2. The DNS server searches its massive directory and returns the specific IP address back to your browser. Step 3. Armed with the actual machine address, your browser bypasses the name entirely and connects directly to the server IP to load your web page. And the craziest part? All of this happens in milliseconds.
Which brings us to section 4, essential troubleshooting commands. Time to fix some network issues.
Because things will break, right? And when a domain name isn't resolving, you don't just guess, you verify. Your 2 primary utilities for manually querying DNS records are nslookup and dig. If you type nslookup google.com in your terminal, it will bluntly tell you what IP address that name currently points to. Now, if you want more granular data, like seeing the exact servers queried and the time it took, you use dig google.com. While nslookup is awesome for quick checks, dig is deeply loved by network administrators for its super comprehensive output. Let's frame up a real-world troubleshooting scenario. You just deployed a brand new update to your company's web app, but customers are complaining that the application is unreachable. They type the URL and nothing happens. As an engineer, your first instinct should absolutely not be to just restart the servers. Your first step should be to test the name translation. You drop into your terminal and type nslookup myapp.com. If it comes back with no IP address or the wrong IP address, you immediately know your servers are fine, your DNS is what's broken. So the crucial point is knowing where to look next. If your nslookup or dig commands throw an error or return incorrect info, you investigate 3 main culprits. First, a domain issue. Did the company forget to renew the domain name registration? I promise you it happens way more often than you think. Second, a wrong DNS record. Did someone make a typo when updating the IP address in the settings? Or third, a provider issue. Is there an active outage with your DNS hosting provider, like AWS Route 53 or Cloudflare? By checking these sequentially, you systematically isolate and crush the bug. Finally, Section 5, Session 6, Practice Tasks. Let's test your knowledge. Okay, here is your mandatory checklist to complete before moving to the next module. I need you to open your command line and do the following. Number 1, find your own IP address using IPA or ipconfig. Number 2, use the nslookup command on your favorite website. Number 3, use the dig command on that exact same website and compare the outputs. And number 4, solidify your understanding of private versus public IPs and why NAT is so vital. This hands-on practice is absolutely essential. It's exactly how these concepts become second nature. To wrap up today's explainer, I'll leave you with this final, slightly terrifying thought. Without DNS silently working in the background, how many IP addresses could you recite right now to survive on the internet? Could you even check your bank account or load a single video?
It really puts into perspective how vital this invisible phone book is to our modern world. And that is it for Session 6 of CloudBridge Tech Labs. Be sure to like and subscribe so you don't miss our upcoming deep dive into NAT and subnets. Get those practice tasks done, and I will see you in the next explainer.